I have ft cosine of 1/2 d theta and ft sine of 1/2 d theta. Over here, I'd have the same thing. Horizontal components cancel out, as just mentioned. And what we're left with is 2 ft sine of 1/2 d theta is equal to mass, actually dm, times acceleration. Now, theta here, we're looking at this infinitesimally small bit of mass and an infinitesimally small bit of string right there. So this angle is actually considerably smaller. It's also d theta to give some indication that it's infinitesimally small. What do you know? Small angle approximation. So this is close enough to ft times 1/2 d theta is equal to a dm. Because the net force is acting towards the center, it is a centripetal force, so therefore the acceleration is v squared over r. So I'm left with the 2's cancel out, I'm left with the tension times d theta is equal to v squared over r dm. Let's see. I know that dm, if we assume a constant linear density, let's do it this way. So if I let that be my linear density, that's, if it's uniform, that's equal to the mass times divided by the entire length, or dm dl. dm, therefore, is my linear density times dl. dl is just this arc length right here. And based upon the relationship between angle, arc length, and radius, what does dl equal? So dm, oh, I have it right here. So that's equal to mu r d theta. And I can take that, pop that right into there. So my tension, so my tension, d theta, is equal to v squared over r times mu r d theta. I conveniently have things that will cancel out here. R cancels out, d theta cancels out. I'm left with tension is equal to v squared over mu, times mu. V squared is equal to tension divided by mu. Therefore, the speed of a wave is equal to tension over the square root. Try that one again. The square root of the tension over the linear density. This is the speed of a wave traveling along a one-dimensional path. Now, perhaps you're thinking there's no such thing as a one-dimensional path, at least not that we could see. But if the length is much greater than either of the other dimensions, then what is it, width or depth, then you can approximate it as one-dimensional, such as a string. Questions at the moment? This is a string vibrator. We had other ones, but they kept breaking down. They were old. So I did a search for my office for string vibrators. These don't come up. First ad was from Adam and Eve. Kept waiting for a call from administration, wondering why I was doing a search on that stuff.
Why is it called a sine wave generator?
That because it basically our electricity is a sine wave or a cosine wave.
Oh.
That will do it just at a different frequency. So it's vibrating up and down at 60 hertz, which is US standard. As I apply tension here, there's I get different patterns. That is known as the second harmonic. Keep that from moving. First harmonic. Take off some of the tension. Second harmonic. Third harmonic. These are known as standing waves. Let's see if I can get that back again. That's second harmonic. Anyway, what's happening is a wave is being sent down to here. It hits this fixed point right here. This is not going to move, and then it bounces back. And so I got waves going in both directions, and they'll interfere with each other. Keep that off for just a second. I can and because of the short distance here, I need to tie this up a little bit. When I was filming this, doing a video version of the lab, there's two labs I had to cut the most profanity out of. This was one of them because things just kept going wrong again and again and again. All right, that looks like it's tilted up some.
A little more. A little bit more. Yeah.
All right. All right. Obviously, we don't have a standing wave going on right here. We do have, this is called a node where it's not moving, anti-node where it's moving the most. But I guess it's partial standing wave. I got a node right here, but this is not anything in particular. So let's add some more mass, see what happens. That's somewhat stable. We have the node over here is a little bit, need to add a little bit more.
It seemed to be the most stable when it was just the big weight.
Pardon?
After you put the little weight on it and then took it off, it became stable
Oh,
with just the big weight. Well, never mind. It was stable.
those days are over. that's not too bad. It's got a little bit of a pulse there, so we're really close, but just slightly off. Let's see, if I add 10 grams, what does that do? That makes it worse. All right, let's just pretend that that's legitimate right there. Now, as you know, and you do know, a wave, basically that's a full wave right there. So and I mean, assume you can see it with a black background. All right. So we basically have a full wave going from here to here. So it goes up, down, and over, up, down, over. The way that it's typically drawn is something like that. These two loops here are supposed to be the same size. This is the antinode and a node. So my wavelength here is the same as basically the vibrating distance.
Is the antinode the peak or just any point in between?
It's the antinode is the maximal displacement. And also be aware that this is constantly peaking and then going down to the other side and back to the other side. So it's zipping back and forth really quickly. So there is a point in which the string is actually just perfectly straight. And if you watch that video, it turns out that the frame rate of that camera is 60 frames a second. And so when I'm filming this, it basically looks like the string's not moving at all. I did that in order to show that it was vibrating. All right, that's looking like about 83 centimeters. So the distance from here to here is 0.83 meters. So my wavelength is 0.83 meters. This is a second harmonic, by the way. I know the frequency is 60 hertz. So the speed of my wave, which is distance over time, which is lambda times the frequency. The speed of my wave is 0.83 meters times hertz. So what is the speed of the wave as it travels along that string? Is any of this actually getting picked up? Oh yeah, it is. It is vibrating back and forth if you happen to be watching this on video. But if it's like the experience early in the lockdown, it won't look like it's moving. So how fast is the wave traveling along the string?
49.8
Units.
meters per second.
All right. I know that should be equal to the square root of the tension over the linear density. Now I happen to know what the linear density is of that approximately. We'll see how close we get. The linear density of it should be about 0.001 kilograms per meter, give or take. And so the tension is just, since it's an ideal string, it's just the weight of this, and that's 200, and I'm going to trust the manufacturer. So I have 0.25 kilograms. So what is the weight?
Newtons.
2.45 newtons. So plug it in here, I get 49.8 squared is equal to 2.445.
2.45.
45 over mu.
I used 9.8.
Probably good enough. That mass probably is a quarter of a kilogram. So mu is equal to 2.45 divided by 49.8 squared. What do we get?
.000987 or 9879.
Pretty darn close. I need to grab something from my office. I'm just gonna let that run. All right, so as we have these waves going back and forth, we have a wave being sent down, hitting the boundary, bouncing back, interfering with itself. To give an illustration of this, I took two waves that were very similar to each other. And hopefully at a quick glance, they look the same. But if you look more closely, they end in a different spot. They both begin at the same place, but they end, this one's still going down, and that one's hit the bottom and starts back up. So they're just slightly off of each other. Do you agree? Okay. I took the blue one and I etched and I put it onto the transparency so that they line up. So if I had both waves at the same time, we start them off. So both waves at the same time, they start out well in sync, but notice they start getting farther and farther apart as you go. You got the purple and the, I guess, black lines that are getting farther and farther apart. If I added these waves together, I would get this. This is the sum of the waves. The others were peaking at 1. They add them together, we're peaking somewhere around 2, but it's getting smaller and smaller. And if I took this and extended it, so it just kept going, it would look like that. So you have this where the sum of them is bigger than what we started with. This is constructive interference. And it's some where it's smaller than it was destructive interference. Now we can show that a different way. Oh, there we go. Oh, there it is. Bookmarked. So now, let's see if we can actually get sound. 440 hertz. So basically we have this, the speaker in there is vibrating back and forth 440 times a second. As it presses in one direction, it pushes air molecules really close to each other. As it pulls, as the diaphragm pulls back, you get less, what's called rarefied air. And so your eardrum's being hit by pressure wave, lack of pressure, higher pressure, less pressure, higher pressure, less pressure. And that's the way our brain processes it. I guess anyone of you tone deaf?
Not that I know.
Okay. All right, so you just heard that sound. Here's 439 hertz. occasionally I have students who can't, those are very, that's 439. That's an add, and that's 440.
It all sounds the same.
Okay. So, but they're really close to each other. Most people cannot hear the difference between them, especially if I made them even closer, like 439 and a half. We would get this type situation here where they're very close to each other. But I would expect if I played them at the same time, something like this would happen. So what that sounds like, 440, 439. So we have what's known as beat frequency, that when I play 440 and 439 hertz, well, think about the time between them. Here's 440 again, then 439 on top of it.